In addition to a t-test, we can also use an f-test for linear contrasts. Specifically, we can use the f-test to test hypotheses that look like this, where we're testing if our contrast, the sum of all of our contrast coefficients times the population means of our factor levels is equal to 0, versus the alternative hypothesis that this contrast is not equal to 0. Now you might say, well, why are we conducting a hypothesis like this? Because in this case, the hypothesis has to be that the contrast is equal to 0, so it seems more restrictive than the t-test. And the answer to that is something that it will take us a little bit of time to see. But in short, basically the f-test allows us to see how we can partition the variability in our amongst our treatments partition the variability of our treatments amongst many different contrasts. And from that we can gain additional insight into what's going on in our study. So let's talk a little bit about how we conduct such an f-test. So in the same way that we can find the sum of squares due to our treatment or our factor, we can also find the sum of squares due to a contrast. So the sum of squares of a contrast, which we'll write sub c here, is equal to the sum from I equals 1 to a of each of our contrast coefficients times our sample means. We take this sum, this whole sum here, and we square that, and then we divide this by 1 over n, that's our sample size for each group, times the sum from I equals 1 to a of our contrast coefficients squared. So this will give us the sum of squares due to this particular contrast. Our F statistic is defined as the sum of squares contrast divided by 1 divided by the mean squared error. Why do we take the sum of squares contrast and divide it by 1? Well, remember, in the F statistic, it's the sum of squares divided by its degrees of freedom to get the mean squared. And so the degrees of freedom for this contrast is 1. So this is the same as saying the mean square of this contrast divided by the mean squared error is our F statistic. Now, if the null hypothesis is true, then we would say that this follows an F distribution with 1 degree of freedom in the numerator and big N minus A, so our total sample size, minus A, the number of levels, degrees of freedom in our denominator. Let's see how we can perform such an F-test for the coffee brewing example. So in the coffee brewing example, remember that our null hypothesis is R the average of mean 1 and mean 2, or sorry, is the average of mean 1 and mean 2 equal to the average of mean 3 and mean 4. So the contrast coefficients are 1/2, 1/2, -1/2, -1/2, and then for mu5, the contrast coefficient is 0. This is our null hypothesis, and then the alternative is two-sided, so that would be a not equal here. So our sum of squares contrast, this will be a little bit long, is going to be 1/2 times 14.023 plus 1/2 times 18.421. That's our sample mean for the second recipe, minus 1/2 times 18.004. That's the sample mean for the third recipe, so our estimate for mu3, minus 1/2 times 22.746 and the next coefficient is 0, so I'm going to omit that. So we add all these up, and then we square that. So this really is the negative 4.1 that gets squared. And then we divide this by 1 over 3, that's our sample size 3, times our contrast coefficients squared and added up. So that would be 1/2 squared plus 1/2 squared plus negative 1/2 squared plus negative 1/2 squared and plus 0 squared. That's our fifth one. I'll just put it in there because it's quick and easy. And again, this here in the denominator comes out to a quarter plus a quarter plus a quarter plus a quarter, so that's 1. So our denominator here is really just 1/3. And our sum of squares due to contrast comes out to 51.74. So our observed F statistic for this hypothesis, we write a little f for the observed statistic. It is 51.74 divided by 1, divided by our mean squared error, which was 9.842, which comes out to 5.257. Is this a large F statistic? Yes, it looks relatively large. We compare this to an F distribution with 1 degree of freedom in the numerator and 10 degrees of freedom in the denominator. We want to find what's the probability we would observe a random variable that follows an F distribution with 1 degree of freedom in the numerator and 10 degrees of freedom in the denominator that's greater than 5.257. And this comes out to 0.0448. This is the exact same p-value that we got from the t-test, and so we have the exact same conclusion. Notice too that the square root of 5.257 is our t statistic, which was 2.2929. So the question again is, if we're getting the exact same results from the t-test and the f-test, why learn both? And again, the answer lies in the ability of using this concept of sum of squares to partition the sum of squares treatment into sums of squares due to multiple different contrasts. And that's where we will turn our attention to next.